Hi there, and welcome back to Triplicate. And moving on with our, move myself out of the way, radical synthesizer called Heresy. And you'll see when I have the camera above it, but I've actually modified the logo now, so it has a border and it looks a bit better anyway. I'm just playing with it. So I realise I have not managed to get too many videos out towards the end of December, what with the festive season and not being well and other things. And also I have been working on the software, trying to get it sort of the bare bones set up, if you like, the PC bits set up. Now we had a look at creating a thread to run the software in, and we did that successfully, and we had a look at ASIO and getting that working. We got that working, but there's been a bit of work to get them together and to get the reading of the musician interface working correctly, and stupid bugs. And once you get into multi-threaded things, bugs are so much harder to track. However, I seem to have got that far now, so let's have a look at where we are. Okay, so here we are. Let's fire this up. And it takes a long time to start for some reason. Okay, so it's opened the input port and it's thinking about opening the ASIO, and it's done. And you can hear it's crackling a bit. That's because the Camtasia screen recorder seems to grab up all the processing power. Might try and do something about that. Right, so here we have rotation, position and speed, and this is super slow because all the messages are getting stuck in buffers again because it's not getting any processor power. However, it works. I'll have to point the camera at the screen and show you working on its own, because it does work fine. And here we have the string, and the bottom of the green bar is the finger position, and the top of the green bar is the top of the string, valve voltage, and as you can see, that works again with a terrible delay because all the messages are getting stuck in a huge FIFO somewhere. The joys of Windows. And I can't get it to shut down just on the window close sensibly, because it just doesn't shut the thread down and it crashes. So I have to, it stops, so that stops the audio thread, and I had all sorts of other troubles, which is why it's printing out messages. So now it's stopped the audio thread, I can safely stop the program. And I also found, which took me a long while to find, that the buffer switch, you have to fill its buffer in this function. So what I've been doing, output next buffer just copies data I've already put in another buffer into the output buffer and sets the buffer empty as true, and the audio thread, this is it, just loops around this loop, and if it finds the buffer as empty as true, it generates sounds, generates a new buffer. which probably adds even more latency to the process. So I am going to investigate the latency now. Okay, so if you look at this line here, I have now used the string 0, string 1 value to control the amplitude of the sine wave. So when I plonk my finger on that string, the sine wave will start sounding, and if I lift my finger, the sine wave will stop sounding. So the latency is the time between that string hitting the contact at the back and the sine wave actually coming out. So shall we see how that goes? And I'm going to have to go over to using the camera because the Camtasia screen recorder takes up all the processing power on my computer. Okay, so let's run this up. I'm just going to start this off camera here. And okay. Okay, so you can hear very quietly it's playing, and if I okay, so when I hit the copper strip with the string, you can hear it makes a sort of clunk noise, and then obviously you can hear when the sine wave starts. So we want to measure the difference between those two sounds. So we have here our trusty microphone, which will sort of bend down a bit so it's a bit better. Okay, a bit of a fight, but we have Cool Edit in record mode, and we have this guy going, so let's see what happens. Okay, stop. There we go. Towards the end there we have some useful stuff, so let's take a look at that. Okay, so here we have a lot of stuff before the stuff we want. Let's just crop that to there and see what we've got. Stuck in there, so that clonk is the string hitting the copper strip, and that is the So you can see the 1 kHz there, and you can see the percussive noise of the string hitting there, but it's hard to see where exactly the 1 kHz starts, so we need a bit of a rethink there. Let's okay, so I have strung a wire between my output mixer and my input mixer, which has grounded the two grounds together, so there's a bit of hum happening. And now if I turn my sound on, hit my string, I get the sine wave coming through there because the microphone is turned off. If I turn the microphone back on, come on, you can see that. So if we were to turn the right of the microphone down, panned the wrong way, never mind, we get right channel from the microphone. I'm just tapping the microphone here, and if I were to grab the pan on, what are we on? 3 and 4. No. Right channel from the microphone, left channel from the beep. So if I now record some of that, we should be able to separate the sine wave from the noise of the string. Whoop. hitting the bass. So I shall do that and promise no more dodgy hand camming. Okay, we've recorded some, and you see the top trace is the microphone getting the string hitting the copper strip, and the bottom trace is just 1000 kilohertz or so tone. So we can zoom in. We zoom in a fraction more. Right, so I guess that clunk there is the string hitting the, oh no, there goes many. That spike there is the string hitting the copper strip, at which point we want it to start, but it's actually starting there, and that is, if we look down there, 41 milliseconds later. So I think we want to reduce that. We certainly need to reduce that. That is far too much, and if you listen carefully you can hear a delay. We want to be near 10 milliseconds or less. So let's see what we can do about that. Okay, and here I have a little text file I print out, which prints out what appears on the memo screen plus a bit. So this is telling us, right, the buffer size, well, it tells us there's 2 inputs, 2 outputs, we know. The buffer size can be 64 to 2048. Preferred is 512, which I think is the default. Granularity is 8, and presumably that means the buffer size can be set in multiples of 8. The sample rate is 44100. Okay. And it says the latencies are 764 input and output. Not sure how it works that out. Okay, so we have seven six four samples, and each sample is 1/44.1 milliseconds long. We get 17 milliseconds latency. So that will probably be alright, but we're seeing 40 milliseconds. So we need to look into that. Firstly, we'll try and reduce that buffer size from 512 and see what that gives us. And I need to figure out how to do that, so I will do that and bring you back. But in the meantime, should we look at the way we're actually writing our code to see if we're introducing unnecessary latency in the way we're doing it before we start trying to reduce buffer lengths. Okay, so here's what I am doing now. There are 2 buffers. The way RCO works, there are 2 buffers, A and B, and it's outputting one buffer while you have time to fill the other buffer, so you get a nice continuous stream of audio. So this is the light red column here, and with time down, so it's outputting buffer A number 1, B1, A2, B2, A3 and B3. The numbers are just identify the contents of the buffer. When it gets to the end of a buffer, so for instance here it's finished A1 and started B, so that means buffer A is available to be refilled. So what I'm doing is copying pre-calculated audio data to A2, and you can see it doesn't take the whole of the time of the buffer, otherwise things really will go wrong. Once it's finished B1, I can fill the B buffer up with the audio for B2. But what I'm doing is, in the switch function, the buffer fill function in the ASIO, I'm simply copying data from an existing buffer that I've calculated, which is the light blue column. So here, once it's done its copy for B1, it calculates the next buffer, which will actually be A2, and then once A1 is finished, B1 starts and it copies from the calculation buffer A2, and so on. So here we have a built-in latency. It's always copying one buffer behind and calculating two buffers behind. So the green dots on the left are the input from the input packets of data from the player interface. So let's consider what happens when we get this one, this green dot here. And I've put these green dots sort of 2/3 the way down each buffer, but they don't necessarily appear. They appear every 3 milliseconds or so. They don't necessarily appear once a buffer. In fact, there might be a buffer time with no green dot in, or there might be a buffer time with 2 green dots in, depending on the buffer length. So we have got, well, in our example, we've pressed the string here and here. It's saying, hey, turn it on, turn the audio on. Well, it can't actually do that. It can't register that till the next calculation period. So we're playing A1 here. We come down here, we copy the previously calculated A2, that's here, and now, oh yes, we can calculate B2, and this B2 can reflect the fact that we've put our finger on the string. So we come down here and it copies B2 and it actually starts playing B2 here. So that is what, 2 and some buffers after the finger has hit the string, and it's got the message that it's actually reflecting that in the audio. The reason I decided to do it this way is because, okay, this outputting samples to the buffer is done in hardware, a DMA or something. This is done in the ASIO callback, which it says is an interrupt, and this is done in my main sound generation thread. So we have to be very careful how we access data between this main thread and these interrupt functions. Here it calculates the little buffer I use to calculate it, if that makes sense. And when it gets to here, it's done calculating it, and in the interrupt it's safe to copy it, and the interrupt sets the flag when it's done. So when it's done copying, it's safe to go back calculating. So that's a reasonably safe way of doing that. Now if we try and calculate our samples in the actual interrupt functions here, it looks like this. That's fine. We can do that, but we have to access this data here from the player interface, which will appear in the normal thread. So it could possibly be that this green dot could be here, and while I'm trying to update the data from the player interface, the switch function interrupts it, and the data here will be indeterminate unless we're not very careful, if that makes any sense. So we're going to have to do this because it saves us a whole buffer. So here we get our input and it gets calculated A2 here, so we're only one buffer and whatever behind actually getting the input. So this is worth doing. It saves us a whole buffer's worth time of latency, or 512 samples at the default. So we'll implement that and see how that helps us. Okay, I spared you the process of me recording this data, because I showed you it the first time I did it. So here we have one channel. This is the microphone recording the string hitting the copper strip contact, and the bottom channel is the 1000 kilohertz. Also sine wave starting. And I've been through these, and you can see these numbers on here. These are the millisecond delay latency between the string hitting the contact and the sound starting, and we can see we get numbers between 30 and 44. So firstly, why the difference? So here is the actual, or nearer the actual situation when it comes to our readings from our player interface, and there are around 4 per buffer with a 512k buffer, because it's a 512k buffer is around 12 milliseconds, and one of these arrives every 3 milliseconds, one of these readings. So you can see that is then more likely the situation. And you see I've put them red here. You imagine pressing the string, and string not pressed onto the contact is green, and string pressed onto the contact is red. And you see that could happen anywhere between here or here. So there is one buffer's worth of variation, 12 milliseconds worth of variation in these readings, depending on the arbitrary point in the buffer output, particular buffer output, when it gets the string on message. So that's why there's this variation in the readings between 30 and 44, and none of this is hugely precise. So it's 14, not 12. So now let's look at this situation. That was the situation where we had a buffer. We were using a buffer to store the calculated values, and now let's look at the situation as in here, where we're calculating them straight in the switch function. Okay, and you can see here I haven't, some of them were iffy readings, so I haven't written the numbers on from them all, but here we can see we have between 21 and 30 or so. So that's between 30 and 40 or so. So it is 10-12 milliseconds better. So we're definitely better going with the calculating our samples in the switch function. So now let's have a look and see if we can reduce the buffer size and make this even better. Okay, so it's easy to set the buffer size. You just, when we call SIO create buffers, we just have SIO driver info, which is our way of collecting all the information together. So that's set by us, current size, and that's what you get. So I tried it previously. This is with a 512 byte buffer, and these were the numbers I got. So this is the previous readings I took for the simple case, and working the samples out in the buffer switch functions. So this is the 512 sample buffer. These are the readings I took previously. So I then went ahead and took some more for 256, and you can see, as you expect, these readings are somewhat less, but still maybe a bit too much. We want to get them a bit less than that. So shall we try 128? Okay, and even less, and heading down towards 10 milliseconds, where I think we'd be happy. I don't think we're going to notice 10 milliseconds delay between playing and the sound changing. But go on, it'll do 64, so we'll try 64. And here it is, and you can see we're down into single figures for some, and the maximum is about 12. So I thought, well, we've got some numbers. I guess the physicist in me I thought, oh well, we'll put them together and make a graph. So here we have a graph. So I've simply put the readings in, taken an average, and then plotted it against buffer size. And you see it's actually a straight line, which is what we would expect, apart from the 64 reading. Don't know why that. It should be, I guess, one lower, should be 8 or 9, but who knows, I don't. And if we follow that line down to no buffer, we would get 6 milliseconds for delays in sending the data from the player interface. And I realise it's going through an optical from the digital to analog converter through an optical interface, which probably introduces another couple of milliseconds. So we're happy with that. 64 we're going with, and if needs be 128, because there's only a bit more. Okay, well that's about as far as we're going to go on this video, and it seems to have been a bit of a struggle, a long haul. I guess about half an hour for you and about a week and some for me, but it's stuff I'm not familiar with, and we've only got to do it once. So now we can start moving on and doing the fun, interesting stuff. And we have created a functioning musical instrument. Whoop. Sorta, kinda. And it only plays one note, and that not very well, but it's a start. And on that exciting note, I will sign off, so it's goodbye from Triplicate. Goodbye.